So then let's go to the next section, which will be about logarithmic functions. That naturally follows basically the exponential functions, because we asked this question, and basically this is a different version of the question that I asked at the end of the exponential functions explanation. Consider an equation of the following form. So suppose you want to know, we have the equation e to the power x equals some constant a. So the base of the left-hand side, right, is this constant 2.7, etc. So this is just the natural exponential function. And suppose now indeed we know what a is, so we know the value of this right-hand side, a, this constant, but we do not know what x is, and of course we want to solve for x. Now the first thing to notice is that, of course, e to the power x, the exponential function, has a positive domain, right? So it can never be, whatever x you put in, the answer will never be negative or zero even. So the range of the exponential function was only the positive number, so this question actually only makes sense if a is a positive number. So the question is, to what power should we raise this number e in order to obtain a? And the answer to that question is by definition the logarithm, or rather the natural logarithm of a. And we denote this by ln of a. So the log of a, or ln of a, is the answer to that question. So the definition here is e to the power the log of a equals a for any positive number. Or in other words, log a, that's the power to which you need to raise e so that we get a. That's the definition. So now let's see how we can work with this. So again, here you see this graph of the function y equals e to the power x, or the exponential function. And suppose indeed we ask the question, for what value of x will this exponential function reach a height y equal to 2? So what would you do? We would look in this graph, we would look at the height y equals 2. It's over here basically, right? And we figure out, what x should we put in to indeed make sure that the exponential function e to the power x reaches height 2. Well, if you look at it in this graph, we see it's somewhere between 0 and 1, or more precisely, it's closer to 0.7. So what we learn from this is that log 2, ln of 2, indeed is more or less 0.7, or here is a little bit more precise answer, 0.693 as by approximation the log of 2. So log of 2 itself is the exact value, and we can approximate it up to any number of digits that we would like. And so if we raise e to the power log 2, then we get 2, right? That was the definition. So again, e to the power x is always positive, right? So this graph of e to the power x is always above the x-axis. And since e to the power log a by definition equals a, the log of a can only be defined for any positive a's. So a equals 0 or a equal negative will give an invalid question essentially. Let's have a look at that. So what does that mean in some examples? So suppose the question is, what's actually the log of e to the power 3? So the question is, to what to what power should we raise e in order to get e to the power 3? Well, we need to raise e to the power 3 to get e to the power 3, right? That's a tautology almost. So the log of e to the power 3 is 3, and that's the power to which we need to raise e to get e to the power 3. Similarly, in the second example, the log of 1, so what's the log of 1? Well, e to the power 0 is 1, right? Anything to the power 0 is actually 1. So 2 to the power 0 is 1, or 10 to the power 0 is 1, and also e to the power 0 is 1. So the log of 1 is actually 0. And then what's the log of e? Well, of course, e to the power 1, that's e. So the log of e, that must be 1. A log of 2 we already encountered in the previous slide, so that was this number approximately 0.693, because indeed e to the power 0.693 is more or less 2. And if you use your calculator, you can actually compute that number in a more precise form. And if you ask what's the log of -5, well, then that's not defined. We cannot input -5 under the logarithm. That gives an error. So the domain of the logarithm is actually only the positive number. We cannot have 0 and we cannot have -5. So there are some rules, some computational, calculational rules involving the logarithm, and I've put some of them here, the most important ones. So the first one says, well, the log of a product, in this case, the log of two positive numbers x and y, so the log of x times y, that's equal to the log of x plus the log of y. So in a way, the law converts products into sums. Log of xy equals the log of x plus the log of y. So you may learn that by heart. I think that's a good idea, but we can also derive it. So in a bit I will actually go to paper and show why this is actually true, a different reason why this is true. In a similar spirit, the log of x divided by y, so the log of a quotient, with again x and y, two positive numbers, is the difference of the logs. So the log of x divided by y equals log of x minus the log of y. If the third example, you look at the log of a power, so in this case x to the power p, the log of x to the power p, that equals p times the log of x. So if you see a power under this logarithm, you can actually take this power and put it in front of the logarithm, which is going to be very useful. And finally, some things that basically we already saw. Log of 1 is going to be 0 because e to the 0 is 1. The log of e is 1 because e to the 1 is e. And by definition, x equals e to the power log of x, and vice versa, the log of e to the power x equals x. So there's two equations which are not true, which are written down there. So that's sort of a bit dangerous, I guess. So you might fall. If you think you might fall prey to having seen this and then believing this is true, just put a big cross through them, because those two equalities are not actually true. So don't fall into that trap. So let me then go to a paper to actually study two of these examples, so the first one and the third, to see why those are actually true. So the log of xy equals log x plus log y, and the log of x to the power p equals p to the log x. So let's see why that's true. So here we are on paper. So we recognize that xy, x times y, with x and y two positive numbers, we can actually write that as e to the power of the log of xy. Right? That's by definition. This is the definition of the logarithm, as we saw. But you can also say, well, actually, I can also write x in a different way. I can write x as e to the power of the log of x, using that same definition. And I can write y as e to the power of the log of y. But if I multiply two powers, then you know what to do. You can actually add up the two exponents, right? So this can be nothing else but e to the log x plus log of y. If you forgot about those rules for computing with powers, have a look again at the appendix of the first week's slides or in the book. So what do we see? On the left hand side, e to the power log of xy equals, on the right hand side, e to the power log of x plus log of y. Well, this can only be true if this power is actually the same as that power. So we learn here that the log of xy indeed is the sum of the two constituent logs, log of x plus log of y. Similarly, if we look at some x, where x is a positive number, to some power p, Well, of course, by definition, again, we can write this as e to the power log of x to the p, right? But we can also see, well, this actually can be written in a different way. We know that x is e to the power log of x. So this itself is x. We need to raise x to the power of p. So we are raising this e to the log x to the power p. But the power raised to some power is basically the same as the base raised to the product of those two powers. So this is actually the same as e to the power p times log of x. So again, by those rules followed by powers, we arrive at this final equality. But now again, compare the left-hand side here and the right-hand side, we see that those two things which appear in the exponent must then actually be the same. So we derived here from the behavior of powers that the log of x to some power p must equal p times the log of x, like we wanted to prove that we have in the slide. Okay, so let's go back then to the slide. There we are. So we proved 1 and 3, and of course, if you want to have a look at number 2, that should go basically in a similar way, and you have to take negative powers if you want to do that. So let's get to now an example. So how can we use these facts? So suppose now the question is, we want to solve this equation in x. So the equation here is 5 times e to the minus 3x equals 60. So again, getting to this solution is on the slide. Let me do it on paper, and then we'll come back to it over here. So here's the question. The question is 5 times e to the power minus 3x equals 60. And of course, we want to solve this for x. So we want to know what x solves this equation. So how would we do this? Well, perhaps a good first step would be to divide both sides by 5, so that you get just e to the minus 3x on the left-hand side and 16 divided by 5 on the right-hand side. And now we are going to, so we want to know something about this minus 3x, which appears in the exponent. So now we use our super weapon, which is the logarithm. I take the logarithm of the left-hand side. So the logarithm of e to the minus 3x is just minus 3x by definition. Then I also need to take the logarithm of the right-hand side. Unfortunately, that's a positive number, so we can do that. The right-hand side will be the log of 16 divided by 5. Now we're almost done, because what remains, we want to know what x is, so let's just divide both sides by minus 3. So x equals minus 1/3 the log of 16 divided by 5. So that's a solution, but for x that solves this particular question. So there we are on the slide. So indeed, you see those steps. Well, it's done slightly differently, but a bit longer, I guess. But same answer, so I'm sure this is okay. Have a look at it. Now let's get back to the question that we asked at the end of our exponential function video, which was, well, we had this bank account, a savings account, on which we got this whopping 8% of interest. And we were sort of saving for buying a car, and we put in 1,000 euros into the account. And this function, remember, g of t, was an exponential function which measures how much money will you have in this account after t years. So that was the initial amount, 1,000 euros, times 1.08, the annual growth factor, to the power t. So the question was, can we find the number of years, so the answer for t, and we call it t bar, such that the amount in the bank, or g of t bar at that time, equals 10,000, so that we can buy our car essentially. So we have to solve that by solving basically 10,000, which is what we want to get, equals 1,000, the initial amount, times 1.08 to the power t bar. So again, let's do that on paper, and you, of course, also can see it on the slide. So the question is, we want to get 10,000. We started out with 1,000, and this was growing at a growth rate of 1.08, so 8% per year over t years. And we want to know, well, what's this, the value t bar, which solves this equation. So how many years do we need to wait until this 1,000 euros has grown into 10,000? So let's solve that. Well, first of all, of course, by dividing both sides by 1,000. .08 to the power t bar. And now we need to isolate somehow this t bar, right? So it appears in the exponent. So what's more natural than taking that natural logarithm again on both sides? So we have on the left hand side, that's just the log of 10. That's a number that equals the log of what we have on the right hand side, 1.08 to the power t. But the log of something to the power t can take, of course, this, drive it up here. If you have something to the power, to some power, p in this case, and we have the log of that thing, then we are allowed to actually put the power in front of the log. And that's exactly what we're going to do here. We're 1.08 to some power, t bar. Taking the log of that then allows us to put that power, the t bar, in front of the log. So that's nothing different from t bar times the log of 1.08. So now we're almost there, because how do we get then what t bar is? Well, we just divide by this number the log of 1.08. So t bar equals the log of 10 divided by the log of 1.08. And if you plug that or type that into your computer or into your calculator, you'll find that it's approximately, so this wavy equation signs basically mean approximately equal to 30 years. 30 years. So you have to wait 30 years if you want to buy that desired car. Let's hope it's still on the market at that time. And here you see the same computation basically again on this slide. So we dealt now with the natural logarithm, or in other words, the logarithm relating to the e, right? The base e, and this number, this special number, natural number e, which was 2.7. But you might imagine that sometimes we're also interested in a base which is different from e. So in particular, we might have any number a which is bigger than 0. And now the definition is going to be, if a to some power u equals x, then we would call u, this number u, the logarithm of x to base a. And we would write u is the a log of x. So in other words, the definition is a to the power, the a log of x is going to be x, where x needs to be a positive number. So if you put in, instead of a, this number e, then we had what we had before. So this generalizes basically this natural log to any base a instead of the number e. So for example, if we ask what is the 9 logarithm of 81, then we ask the question, well, to what number should we raise, to what power should we raise 9 to get 81? And then obviously the answer is going to be 2, because 9 to the power 2, or 9 squared. Well, that's 81. And similarly, if we look at the 4 log of 1/64, that's going to be minus 3, because 4 to, well, remember 4 to the power minus 1, that's 1/4. So 4 to the power minus 3, that's 1 divided by 4 to the power 3. And indeed, that's exactly 1/64. So these are A logs. And of course, these generalizations, these A logs, also satisfy similar rules as the natural log that we started out with. So again, if we have any logarithm of a product, it's going to be equal to the sum of the individual logarithms. Similarly, for a quotient, we have the difference between the logarithms. The logarithm of a power, again, we are allowed to put this power in front of the log. And as always, the log of 1 is 0 for any base, because a to the power 0 is 1 for any number, positive number a. And since a to the power 1 is a, so 2 to the power 1 is 2, or 10 to the power 1, that's 10. And similarly, the a log of a is going to be 1. So quite similar rules as we had for the natural logarithm. So do we need to learn all of this by heart? Well, you might, but you might also always just convert any A logarithms that you see into natural logarithms. Now, would that work? Well, we can see here a relation essentially between the A logarithm and the natural logarithm, because, well, by definition, this first line says a to the power, the A log of x equals x. Yeah, that's a definition of the A log of x. But let's take the natural log on both sides. So the natural log, ln, of this a to the A log of x must then be equal to the natural log of x. But on the left-hand side, we have the natural log of a to some power. So we can put the power in front of that log. So we get the A log of x times the log of a on the left-hand side. And still that equals the right-hand side, right? The log of x. So we use this rule. We can, if we take the log of a power, then we can put the power in front of the log. So here the power is the A log of x. You can put that A log of x in front of the log of a. And now we're done almost, because we just have to, this is the A log of x times the natural log of a equals the log of x. So just divide both sides by this natural log of a. So what remains here is the A log of x equals the natural log of x divided by the natural log of a. So there's a direct relation between the A log and the natural logs, just a scaling relation. Essentially, you have to scale by the natural log of that new base that you were interested in, this number a, essentially. Okay. So that's the relation. So if you know that, basically you can always convert one into the other. Finally, what do these logarithmic functions look like in terms of what shape do their graphs have? So let's look at either some g of x, which is just the natural logarithmic function. So remember again, the domain of this function is just the positive number, so 0 is not allowed, hence this round bracket over here. So 0 is not included. You cannot take the log of 0, and goes up all the way to infinity. Or equivalently, because it's just a scaled version of that, the A log of x, which again has the same natural domain. So what does the graph look like? Well, a bit like this. So it's not defined for negative or 0 x. It's defined for any positive x, but it starts out very deep down here, grows very fast at this point, at 1. It goes through 0, passes through 0, and it keeps on increasing, but at a slower and slower and slower rate. So this is what the log of x looks like as a graph. So I cannot emphasize this enough. If you are interested in the natural domain of some function and it does have a log, so remember, if you had a fraction or a square root, that gave some conditions on the natural domain. For the log, likewise, there are some conditions, namely anything that goes under this log must be positive, cannot be zero, cannot be negative. So those are the conditions that are associated with logarithms if you're looking into what's the natural domain of that particular function. Okay, so the last bit will be the last video of this lecture, which will be about inverse functions.